Hi everybody, so I will explain the concepts behind the tangent and velocity problems. So in this section there are two problems that are important, the tangent one and the velocity one. So I will go ahead switch these screens and talk about some ideas. So this one should not be a long one, and this is about section 2.1. Okay. So before I talk about it, since this is the beginning of calculus, we need to ask what is the main part from calculus. Of course, it is an advanced math that uses algebra, trigonometry, geometry to serve certain purpose, right? And before, when you dealt in college algebra, for example, with you usually deal with like a slope or a straight line, and you do the rise over the run, and you say the slope is the change of y over the change of x, which is that rise over run. And here, if you go to this, it's going to be y2, and this is going to be y1, and this is going to be x1, and this is going to be x2. So y2 minus y1 over x2 minus x1. But of course, in the real world, not everything is going to be this way, right? You may be moving something, you need to move something up this hill or something, and it's not going this way. And projectile or something may go this other curve. So if you want to find the rate or the slope there, it's not going to be accurate. How are you going to do it? And that's the question that calculus answers. So in algebra, the way you did rate of change, for example, for a curve, you just did the 2 points and you calculate and you say it is what it is. Then you'll find, for example, for a parabola, you'll find the slope 0 or something, but it doesn't make sense. In calculus, if we look at the same curve, the question changes to what is the instantaneous at that point, right? What is the instantaneous rate? It's kind of instant. So right? So that's what calculus answers. And the two big ideas in calculus that you're going to be working with is differentiation and integration. And these two big ideas are connected with the fundamental theorem of calculus. So I will talk about that as we go through the course, but uh, this is a small introduction that now we're not talking about the change of y. You just take 2 points from somewhere and you calculate. We're going to make zoom like this place. Calculus takes it and zooms, in kind of like here, right? And to calculate what the rate there. And that's one. The second one is we're going to deal with two blocks of differentiation and integration. And these two blocks are connected with the fundamental theorem of calculus. Right. So we'll explain a little more of that as we go. So what is this first tangent problem? the word tangent, and of course in math there is also that tangent like, right, um, function or something, you know. This is something else, the tangent to a curve. We're talking here tangent, which is like, this is a tangent, but I'll show it. Is derived from this Latin word tangents, which means touching. Right? So the tangent to a curve is a line that touches this curve, all right? But it should have the same direction as the curve at the point of contact, all right? So to show that, a simple one will be a circle. So as Euclid says, that tangent is a line that intersects a circle once and only once. So if we do like this point, so this is another tangent line and we can call it L, for example. However, in real life, they are, let's say, a roller coaster, right? It's not a circle and it twists and all that, and you need to do the calculations. So here there are two lines. The first one, L, it crosses it in one point, but it's not in the same direction. And T, it kind of in the same direction, but it crosses in 2 points. Like, all right. So let's talk about the first example to show this meaning that's going to take us to the limit. So find an equation of a tangent line to the parabola. So some of the problems we'll be solving in QA session will be like this. So find an equation of a tangent line to the parabola y equal x squared. And if you, of course, we are familiar with this parabola, it looks like something like this, y equal x squared. And then there is a 0.11. Because if you put x as 1, you'll get y equal 1 squared, which is 1. So we will be able to find this equation as soon as we know the slope, right? Because the tangent of the is going to be a line. The difficulty, of course, is we know only the point P, which is 1, 1, on that here, right, on this line T, right? So we need to find the second point, because you know the idea of the slope that I talked about, the change of y over the change of x. So you need y2 and y1 and x2 and x1. So let's see it here. Here is the function x squared, and here is the 0.11, and we do the tangent line. As you see, with this one, you can do different lines. And one line we can attempt here is the secant line. And this secant line is like I mentioned, you try to cross the graph, just curve it a little bit so you see what happens. Let's say here and here. And we're given a point already, so we come up with this Q point so we can calculate the slope, all right, of this secant line. And as you see, if you're not familiar with this notation, xx squared, of course, what it means is just a function. If you put x as input, you get x squared. If this is a, then this is going to be a squared, because you put a here and becomes a squared. So some of the examples I'll put solved and explain them, and some will just put and solve them this way. It depends on the session. So the change of y, which will be the q, right? The y at Q point minus the y at P point. P is 1 and X is 1, 1, 1. However, for the Q, we don't know. We just say it's X, so Y will be X squared, right? Then we have to start making some guesses on what Q should be. So 1, 1 here. So it could be 2, it could be 2.5, it could be whatever, 1.5, few numbers. We try to stay close, but some number after 1. So let's say we take 1.5. So this will be x2, and this will be y2. Then we get 1.25 over 0.5, and that gives us 2.5. So as you see, depends on how we pick the second line, this number is going to change. So let's investigate this. If I pick x as 2, this is the one we tried, 1.5, we got 2.5. If I pick x as 2, the result from that formula of the slope, I get 3. So you should try it and see. All right. So this is the MPQ, which will be the change of y over change of x. If I get closer, 1.1, the answer will come up as 2.1. So 1.01, right, for x. So how do you calculate this? Just like what we did. So x is 1.1. So you will put it in the function. So you do 1.1 squared, right? Then you set it in the formula, 1.1 squared minus 1 over 1.1 minus 1, right? So you should get 2.1. All right, so if you want to try it in a second. All right, so you should get 2.1. So that's how this table could be. So as you see, the Q or P is 1 and 1. So as we get close to this one here, this X, what happens? You see this number 3 decreases to 1.9, 1.99, 1.39. So it gets close to 2. So this tells us as you get closer to 1, this MPQ is going to be 2. All right. So that's the goal. So this will change. So we need to explain it. This suggests that the slope of a tangent line should be 2. We say that the slope of tangent line is the limit of the slopes of the secant lines. So you can have multiple, secant lines passing through there. And because the Q can vary, it can get closer and closer and closer. So if I zoom in, if this is P, then Q can be these, right? They can get closer. And as these get closer, the slope of this secant line will become a tangent line right at the point or close to it, right? Right close to it. It's going to be 2. So that will explain the limit of that slope of the secant line will be 2 as x gets close to 1. And that's what the table shows. All right, so if you do these in exercises, you see as the x approaches a value, this slope approaches this number, right? So now that we find the slope, we know y equal mx plus b. because it's the slope of, we're looking for the equation of the tangent, which is a line. And there is another way, which is this formula here, the point slope. Since we know the point P, 1, 1, 1, 1, then we can use, and now we know the slope, so we can apply it to this point slope formula and find that the tangent, so this is the tangent at P 1.1, right? And so this is kind of to illustrate the, this idea of the secant and tangent that I already explained. And a little more here, explain it a little more. You can pause the video and see based on what I draw and these examples, all right? So we were able to find the equation or the line of the tangent at the point 1.1, all right? So now the second problem that is important in this section is the velocity problem. And suppose that the ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. So some experiments were done, and Galileo discovered, of course, that the distance falling by any freely falling body is proportional to the square, proportional to the square of the time that it has been falling. All right, so this is kind of you can say like a direct variation, but with a square of the time. And with the experiment, it was found that it's 4.9, the constant. So maybe we can put here. So this is the interpretation, which means some, of course, constant is going to be there. And the constant was found to be 4.9. The difficulty in finding the velocity of 5 seconds is that we are dealing with the single instant of time at 5 seconds, right? So no time interval is being involved. So how do we do this? Well, it's the same thing. We're talking about that slope, which is a rate, which is an average rate, which is a change of y or a change of s over a change of time, right? We're talking about S2 minus S1 over T2 minus T1. And now we need to find out, because we're given just 5, and we need to create this as a kind of a rate in order to calculate it. So we'll say, okay, if it's 5.1, we stay close. We know the goal is 5. So if it is 5.1, right? Then of course, when you do 5.1 minus 5, you get 0.1. And this is time. So you need to find the S at 5.1, which is this. All right. How do we find S at 5.1? We go back to the formula. S is 4.9 T squared. So 4.9 times 5.1 squared. That's this part. How do we find S of 5? All right. We find S at 5 by S equal 4.9 times 5 squared. which is this one. And of course, this difference is 0.1. We find that it's 49.49 meter per second. All right. So this is how the velocity problem works. And one more slide to explain that if you take the time between 5 and 6, so you see 5.1, we find 49.49. But if you make the interval a little bigger, you see how you deviate from 49.49, but you get close to it as the interval gets closer. And that's the purpose from this table, is to understand and compare the result we found with how it is affected with the intervals. All right. All right, so it appears that as we shorten the time period, the average velocity is becoming closer to 49 meters per second. The instantaneous velocity when t equal 5 is defined by this limiting value, all right? And it is 49 meters per second. So as a summary, the goal is 5. You want to find the rate, you stay close. Let's say 5.1. And we will see, of course, when we talk about the limit and derivatives and other things, other ways of calculation. But this is the foundation to understand. Thank you.